Today I'm going to present pretty much two conceptual papers that I have written with my colleague recently. And this was actually arises from my teaching time when I was in Australia, because it's the second time that I got a chance to teach in school. The first time when I was in Malaysia, and there's the second time. And during that time, with my research background and my teaching experience, then I have identified mathematics education research issue that is worthy for investigation. And one of those is algebra instruction. So today my talk is the first part is about learning linear equation, which is about algebra. And the second part is how to transfer that knowledge to learn trigonometric problems that involve algebra transformation skill. Okay. So this is the paper that I'm going to present, the first one. Learning linear equation, capitalizing on cognitive loss theory and learning by analogy. But my focus is only on learning by analogy. Now, learning linear equations sequentially, and why is it important? How do we teach more complex linear equation, multi-state equation, once students have learned simpler linear equation like two-state? A more complex linear equation normally comprises one extra solution step than the preceding simpler linear equation. So the key is, how do we help students to build up their prior knowledge? How do we build the student mathematical knowledge on their prior knowledge? In fact, there is a hierarchical level or schema reflecting differential level of complexity of linear equation. The lower level schema of simple linear equation is embedded within a higher level schema of complex linear equation. So in fact, I know that some of you may come from different background of mathematics, but mathematics actually is about relationship and pattern. So in my previous paper that I wrote about how to classify linear equation, unpacking the complexity of linear equation. So there are a relationship between linear equation, and it is important for the teachers to teach students linear equations sequentially. Now let's look at this one-state and two-state linear equation. So is there a relationship between the two? So in my previous research on linear equation, I used the relational line and operational line to describe the solution procedure of linear equation. And this is important so that they help students to distinguish the type of solutions there in linear equation. If you look at this one-state linear equation, line 1, 3, I call it a relational line, and line 2 is operational line. So this one-state equation has two relational line and one-state operational line, whereas the two-state equation got 1, 3, 1, 2, 3, line 1, line 3, line 5. So there's relational line, and line 2, line 4, operational line. So you can see there are more solution state of this two-state equation than one-state equation. And these two-state equations are more complex than this one-state equation. But the important thing is that in terms of analogical comparison, when you compare these two, you want to direct student attention to the fact that the subset of the two-state equation share similar solution state at a simpler equation. Here, 3, 4, 5, and is similar to 1, 2, 3. They share a similar problem structure, a similar problem solution. And that is very important because one, you can help students to build the knowledge on their prior knowledge. So learning a more complex two-state equation, learning line 1 and 2 only. So it becomes much easier. In terms of cognitive loss theory, they're reducing working memory load. And again, this is just another example. So you can extend this rationale to the relationship between two-step and multi-step, and how to distinguish the solution step. And then you can classify, use the relational line and operational line. And this multi-step got line 1, line 3, line 5, line 7. So 1, 2, 3, 4. 4 relational line and 3 operational line. So that is more complex than that. And again, the subset of this 3, 4, 5, 6, 7 share a similar solution state as two-state equation and the same rationale. And then when they learn this, they only need to learn 1 and 2. Okay, sorry, the next one. So as you all know that this learning by analogy, the basic rationale is that you compare a pair of isomorphic work example. That means both of them share similar problem structure, therefore solution procedure. So if you look at these 2 linear equations, the only difference is one is in decimal and there is in whole number. So actually you can have 1-to-1 mapping between the two. And in this theoretical paper, so what have I proposed? And as I had explained before, there is the key concept of my theoretical papers, highlighting analogical comparison between a subset of the more complex linear equation and the simpler linear equation. So unlike the traditional analogical learning that you compare and learn the problem, a new problem, exactly the same, but I wanted to draw the student attention to the subset or the complex one to build on their prior knowledge or the simpler one. So our aim is to design instructional method for learning complex linear equation by capitalizing on prior knowledge of the simpler equation. Now, how do we do this? Analogical learning. So in my paper, I propose 2 phases. This is a classroom practice, how to help students learn linear equation. A teaching phase and an acquisition phase. So the teaching phase, you want to teach a more complex equation, just say 2-state equation, and the teacher will attempt to link this 2-state equation to another simpler linear equation, such as 1-state equation. So the first step the student need to do is to review how to solve simpler linear equation. While the student has already learned this, but it is very important that you need to strengthen the prior knowledge before you introduce the 2-step. And then you go on to explain the 2-step. Now, how do I do it? So in terms of analogical comparison, there are a few things that the prior studies has indicated to facilitate analogical comparison for students to learn. One thing is that, as you know, that I put the 1-state equation and 2-state go side by side. And this is important because a lot of private studies, a lot of earlier studies on analogical comparison, then the learner need to retrieve the prior knowledge. And that retrieval is caused a big problem, a huge challenge. So by putting it side by side, you reduce or you eliminate the need for the learner to retrieve the prior knowledge. And that will reduce the cognitive demand on that subsequently. So the next thing that, to help them to engage in active analogical comparison is to label it. I label 1, 2, 3, 1, 2, 3, 4, 5. And this is an important cue so that you will help them to engage in 1-to-1 mapping between the two. And in my case, here, line 1, 2, 3, line 3, 4, 5. And then also the detailed solution state. So these are the important thing. And of course, ultimately, as I explained previously, the main purpose is to get the student to notice that a subset of the complex linear equation share similar solution state as the simpler linear equation. So ultimately, the student need only to learn line 1 and line 2. So this is just a recap what I have, what you need to do as a student, draw the attention to the line, the similar line between the two, and then also they share the solution state, of the subset and the simpler one. And the student can use the schema of the simpler linear equation to understand the complex. So that is the key point here. Now, apart from the teaching phase, in the actual classroom practice, normally for mathematics, to have an in-depth understanding of mathematical concept, you still need to get the student the opportunity to practice to solve the problem. So there is the acquisition phase, another critical phase. Now here I propose each student receives 6 pairs of example that are similar to those presented in table 4. Well, this one is really depend on the teachers, depend on the type of students that you have. So sometimes you may need more, sometimes you may need less, depending on the ability level of the students. So here, for example, each pair consists of a complex linear equation and preceded by the simpler linear equation. So you give them the exercise which are pretty similar to what you had taught them to reinforce what they have learned. So as you can see that this is very similar as the previous slide, table 4. So again, so this one, line 1, 2, 3, line 3, 4, 5, they share the similar solution state, similar problem structure, and you label it. By now that you hope that the student understand how to distinguish the solution state, relational line and operational line, and then so they only need to learn line 1 and 2. So this is just a recap. As I say, that you place them side by side, you label them, relational line and operational line. And then for my case, now in addition to all that, I'm still creating 3 reflection questions. So all this, the aim is to strengthen or to help them to have an in-depth understanding about the comparison, the relationship between the two, and how to learn the complex one by building on the simpler one. So 3 reflection questions. Because the prior studies like Ritu Johnson, some of you may have known, mathematics educator in US, they are always proposing the importance of asking questions, to pose questions for students to think mathematical and reasoning skill. So reflection question number 1, how would you compare these 2 linear equations? Now, the reason that why I use that tip the correct answer, because I'm thinking about in terms of the constraint or the classroom time, because the time sometimes is a bit limited for students, so it just take a little bit shorter time for them just to pick this. And so for this one, 3, 4, 5 of this complex equation is actually similar to 1, 2, 3 of the simpler equation. So the next one, why might it be helpful to compare these 2 linear equations? Because this is important. Because if the students are able to give you the reason or the rationale behind it, so that means they can articulate that. That means they have understanding of what's all going on. So here, as you can see, I think A, B, C, D, E. I think A is correct, B is correct, C correct, D, E, the solution procedure of the simpler linear equation differ from that. So that is not correct. Because it's exactly opposite of what it should be. Because this one will present subset of the complex to share the similar solutions that at the linear equation, a simpler one. Now, reflection question 3, there's a fair bit of it. Yeah, so I let you read this one. So again, so this one, really, you pause all these questions to get them to see the differences and similarity. Even this one, yes, I can identify complex linear equation. They have one extra term. That is important because they get them to see the problem structure, the first line of the difference between the simpler one and complex one. So there's one extra term. It does not allow me to remake, so that is not true. Yeah, I can retrieve this. Yeah, that is true. So to generate this solution is true. Line 4, 3, 4, 5, similar to 1, 2, 3, that is true. Line 1 and 2 do not appear, that is true. Because we want them to know that the difference is that the complex one got 2 extra lines. Learning to solve complex linear equation become learning line 1 and 2 only. So straight away, this one made the student feel that the learning of complex linear equation is not that challenging after all. They only need to learn 1 and 2. Now, out of the 3 reflection questions, which one is the most important one? Reflection question number 3, requiring students to judge the merit of comparing is in part equivalent to asking them to identify the underlying principle that define this learning by analogy strategy. So that is the key point. So if the student is able to articulate to get all that correct, then they will know the rationale underlying it or the principle underlying it. It's just like they'll be able to teach another students about it. So that is important to consolidate their understanding, the whole things. So how can you apply analogical comparison in other math topics? So that is the next paper that I'm going to present. All right, just now I say that I'm going to transfer that analogical learning to the context of learning trigonometry problem. And this is another conceptual paper that I and my collaborator published in 2020, learning to solve trigonometry problem that involve algebraic transformation skill via learning by analogy and learning by comparison. Right, now why am I interested in this? Just now I said previously, when I was teaching mathematics in Aubrey High School, and then I find out this my year 11 students struggle to distinguish how to solve these 2 types of trigonometry problem. As you can see that one of it is having a pronumeral as a numerator and the other one having pronumeral as a denominator. So more specifically, and the student has a difficulty, although by the time that they are in year 11, you have thought that they have learned how to solve linear equation. And so they have already learned how to solve linear equation with a fraction such as this, and yet they still are unable to solve trigonometry problem with pronumeral either as a numerator or as a denominator. Now, more of a concern for the teaching practice, my college will taught how to solve trigonometric problem when the pronumeral is a denominator. They just swap this sign 35 degrees with S. So that was incorrect. So that is incorrect. And because they fall short of conceptual understanding of how to solve trigonometry problem with pronumeral as a denominator. So learning by analogy, as what I have explained in the previous presentation, is basically a comparison between a learned problem and a new problem. So the key point is to build student knowledge on their prior knowledge, which make it easier for them to learn. So we juxtapose a linear equation such as this and a trigonometry problem such as this to facilitate linear analogical learning. So if you put these side by side, then of course, you want the student to notice that. So for the equation with a fraction, and this one fraction is on the left-hand side, and here trigonometry is on the right-hand side, and moreover, this trigonometry problem sine 30 degree, sine 30 degree actually is a number. So all these things, they will cause a bit of challenge to students. So how can these analogical comparisons help them to understand how to build a knowledge on the prior knowledge of solving linear equation with fraction? So what have we proposed in this paper? So we propose certain things which are different from the prior studies on analogical learning. So a mental representation of 3 variants of the sources example instead of 1. So we propose 3. Select 1 relevant source for the target problem. And we also propose the mapping of the relevant source example and the first solution state of the target problem. So this is another feature that is different from the previous studies in analogical comparison. And moreover, and there's one more step, actually, I require the students or the learner to generate a parallel solution state for the target. Okay, let's see. So as I just mentioned, this just recap. So the prior study only subject 1 mental representation of the source, that means only 1 source, but I propose 3 and choose 1 relevant for the 3. And map the relevant one and the first solutions that again, I'm focused here on the subset of the target problem, not the whole problem. And generate the missing parallel solution line. Now, to engage learner or students to actually doing it and write down the solution or solve it, and it has an added advantage for them to think deeply about how to solve this problem. So this is a screenshot that I taken from my paper. As you can see there, so the first step, actually there are a few activities for them to do, and they are presented with 3 equations. And at the focus, the aim is to get the student to see that this equation 2 and 3 is a derivative from the equation 1. So I want them to gradually notice that the difference between equation 1 and 2 is actually a position or the location of the fraction. So equation 1 is on the left-hand side and this on the right-hand side. And the difference between equation 2 and 3 is only the difference between 1 is decimal number and 1 is the whole number. So as you see that this is a gradual process, but the key is that I wanted the student to recognize, identify that the 3 equations share the same problem structure, and therefore they are able to be solved with the same solution procedure. So the second step is then they will need to study or examine the solution procedure of equation 1. And this one consists of 2 relational lines and 1 operational line. And then they generate the parallel solution for equation 2 and 3. So by the time they finish this activity, I want them to have a sense of understanding that all these 3 are the same because they share the same solution procedure. In spite of the fact that, they got different in the location of the fraction and decimal. So the last question, why might it be helpful to compare equation 1, 2, and 3? So this is a really key point. Because, they need to understand that why do they need to do it? And why do they need to do it? So the main aim is to help them to understand that they all share the same. And trigonometry problem where, so this one is just a recap as what I say. So actually I label it and help them to recognize, to use a relational line and operational line so that it be easier for them to recognize the 2 types of solutions that we think solution procedure or linear equation. So once they have seen the 3 source example, and they need to choose one which is most appropriate for them to learn how to solve trigonometry problems with the pronumeral as a numerator. So they choose the one that is the decimal, the last one, the third one, because this one is the closest resemblance to the trigonometry problem with pronumeral as a numerator. And my apology, actually, I realized that in fact, this one, 2, 3, 4, there's another line missing. So once the students are able to express this trigonometry 30 degree as a decimal, and in fact, by the time that they learn trigonometry problems, they would have learned this before. So these are the prior knowledge. So we will expect them to be able to express this as a decimal. So once they have done that, so they will realize that line 1, 2, 3 will share with 2, 3, 4, 5. So that is what we want them to know. And then once they examine this, so they have to generate parallel solutions for the target problem. So we expect the learner to recognize that line 1, 2, 3 are the relevant source examples, share similar line at 2, 3, 4, 5. So 5 is missing here, the target problem. And line 2 is the first solution state of the target problem. And once sine 30 degree is replaced by a decimal number. So really they are using the same rationale as what they have learned with how they choose the 3 source example. So they examine the solution state and then they generate the parallel state for the target problem. And the target problem that they do the analogical problem is only a subset of the target problem. And again, the question, why might it be helpful to compare a relevant source and a target problem? Again, this will help them to have a deep understanding of why they do it, the underlying rationale. Now, expert learner, because in the classroom setting, you always have a student that who might be have a higher prior knowledge in a domain. And in this case, like, you know, if the audience, some of you are mathematics teachers or mathematicians, straight away that you can see that there's a similarity between the two. You notice that this is just a difference between the location. One is fraction and one is fraction on the left-hand side. This is on the right-hand side. And so, you know, once you express this sine 30 degree in decimal, you had a solution, because you can use the same solution procedure to solve this linear equation with fraction, and you apply to solve these trigonometry problems where the pronumeral is a numerator. So the expert learner, they can do it straight away. They don't have to go through all the different stages when they become an expert in this domain. Now, what about trigonometry problem share where the pronumeral as the denominator? In fact, you can use exactly the same reasoning, the same strategy method to do it. So in this case, again, as you see that I present these 3 solution equation, and equation 2 and 3 are derivative of equation 1. And they again, as you see that, you know, all you want to see that it's just a different of the location of fraction, and this is a different of the decimal. And then again, the student examine the solution state and generate a parallel solution state. And then you get into think, why might it be helpful to compare these 3? And then choose one of the relevant one. So the procedure is exactly the same. I'll repeat here. And what I want to draw your attention is that, as you can see, that this is more complex. More complex. So this one, you have line 1, 3, and 5 relational lines, 3 relational line, 2 and 4, 2 operational line. So they are more complex than the previous one, where the pronumeral is a numerator. And the others are all the way that the activity the students are engaging are the same. They need to generate that once they express this cos 60 as a decimal. Again, the comparison actually is between the source example and the first step of the target problem. Is a subset of the target problem, and that's important. Now, again, you always need to think about the expert learner. So the expert learner, actually previous studies has done a lot about expert learner. Expert learner who has a high knowledge, with a substantial knowledge in the domain, and they are able to skip the solution step. So that, you know, it becomes much simpler. If we look at the previous slide, the expert learner, they don't need line 2. The expert learner, they can skip line 4. So they considerably reduce the solution step. And so this one, so the expert learner, they can skip that. And moreover, it's just like before, the expert learner, if you put this together, straight away they know that they are similar. And so they can use the same method to solve both. So that is the expert learner. Now let's look at the learning comparison. And as I mentioned in the beginning of my talk, that for this second half of the presentation, and in terms of these two types of trigonometry problem, the student tend to get confused when to use, how to solve the one that which is a pronumeral as the numerator, and when and how to solve the type that we have pronumeral as the denominator. So how can we help them to identify or to be clear about how to distinguish these two types of trigonometry problems? So that is where learning by comparison come in. So the key point about learning by comparison identifies similarity and differences between the two problems. So we wanted them to look at similarity and differences, and thereby contributing to student understanding of the solution procedure of the both problem, so that they get the in-depth understanding of how the two problems, the solution procedure, are different and the same. So as before, so if you put this together, so what are the difference between these two types of problems? One, the location of pronumeral, and that is the key point, the location of the pronumeral. And of course, this cos 50, cos 90, so they are all trigonometry ratio, like cos tangent. So the student will have learned this prior knowledge again. And because of the difference in the location, then we have this different solution procedure. So you can put this together, so the student will see that this pronumeral as a numerator got fewer solutions, that easier. Pronumeral as the denominator got far more, got a few more solutions that in terms of relational line and operational line, this one got, or if you look at line 2, start with line 2, you got 1, 3, 2 relational line, 1 operational line. This one is 1, 2, 3 relational line, and 2 operational line. So this pronumeral denominator is more complex. So another way to help students to learn this, again, is always try to this analogy. Oh, okay, before I go to that, let's recap. So recap these differences and similarity. The location is one of the key things. Differential number line, so they can see that why one is more complex than the other. One, actually, they need more operational line, 2 operational line, the 2 step, and relational line also more. And similarity, so these two, they are all trigonometry ratio. And then once they replace that, is a decimal number. And the inverse method to solve, because both of them are using inverse method, mean multiply become division, the division become multiply. Okay. So as I say that, the key thing again, bring back to the fact that if the student struggling, still struggle, they can't distinguish those two, then you can start from the beginning. I mean, not really exactly beginning, but you draw their attention to the prior knowledge or how to solve linear equation with fraction and put this together. When you had the pronumeral of as a denominator and the numerator, so what are the differences? So this one will help them to understand the trigonometry problem. Now, conclusion, analogical learning. In my case, what I propose is select one variant source problem among the three and use a subset of the target problem, not the whole problem. A subset is just a linear equation. You look at the subset and the prior knowledge and generate the missing parallel line. So those are the three things that which are new advancement for analogical comparison that I proposed in my conceptual paper. And learning by comparison, let me also say, so this one is important because, you know, I see the students struggle in the classroom. So I think the learning by comparison will truly help them to overcome the long-standing difficulties of learning trigonometry frame. They differ because of the relative position of the pronumeral. Now, in fact, after I have written a conceptual paper, I have collect data. I will collect data in both Australia and Malaysia. So I have submitted manuscript, you know. So I hope that it will publish, and then people get a chance to read that. And also, I have also collected data of learning by comparison trigonometry problem. Yeah, so I hope that they will also in future that people can look at the paper, yeah, for the result. Now, what about other topics? And I find that it is a really useful to use the analogical problem solving. In fact, because algebra is always a challenge for students. In fact, this one that I took it from a book chapter that I written for the mathematics textbook for secondary school that I co-author with a number of mathematics education academic in Australian university. Now, this is very important because the students often do not understand, you know, the variable in the context of algebra. If you 2a, they may not understand 2 multiplied by a. So if you compare this with this arithmetic computation, then the student can see the logic. Then it becomes clear to them. In fact, in the primary, and the student actually can use this, you know, they can draw the 2 rectangle so they can see even clearer, you know, algebra, problem solving, and algebra and arithmetic computation. So the key point is we always need to help students, like, you know, to draw their prior knowledge. And this is very critical because algebra is always a problem, pose a great problem. So you want to help the student to transfer the arithmetic reasoning to algebra reasoning, to transfer arithmetic reasoning to algebra reasoning. Now, this is another one that I haven't really collect data from it. And because I was thinking about this, you know, Ritu Johnson, and then proposed, and they have John Starr and all these top US mathematics education researcher. So they're talking about developing procedural fluency in equation solving. But if you look at this method, these two, and in fact, in Australia, the teachers tend to use this method. You know, they wanted to help the student to simplify the fraction and before, you know, to solve that. But in the Asian context where I come from, and I noticed that, you know, my colleague and I, we will use this. As you can see, and method 1 got fewer solutions and method 2 got more. And you might argue that, well, you know, we shouldn't expose students to all these multiple methods because it depends on the ability level of students, sometimes, they get more confused. But I think it is a very useful thing, to introduce that. Once you introduce the learning linear equation, wherever appropriate, introduce them so that they can see that method one is more efficient. Okay, now others. And this one, again, this is the paper that coming from this paper that I wrote. And a lot of math teachers, they kind of completely underestimate the challenge they pose to students for learn one state equation. In fact, I hardly ever find this sort of equation, 5% s equal to 25, s plus half, and or the decimal number, when they introduce a textbook or how to learn one state linear equation. Again, I say that this is very important. The student can use an analogical as this versus this, and this versus this, and this versus this. So they can see that they all share similar structure and similar solution procedure. So there is the power of analogical comparison. Now, again, just a little bit more, and these two again, the student cannot understand why this one half over p, you write it this way, and you write it, they are the same. But if you put them together, they get them to think about it, then they will reason that, oh, you can have one-to-one mapping, and you share the same problem structure, so you share the same solution procedure. And similarly, here, again, if you have an analogical problem solving, so you have the difference in pronumeral and even the position. And this is on the right-hand side, and this is on the left-hand side. And this one, the students tend to make mistake, because they had a tendency to divide the bigger number as smaller number. They will say s equal to 3/1. So by doing the analogical comparison, you get the student to an in-depth understanding of solving the problem. So this one, actually, this one is from my student, because my unit, is a junior secondary and senior secondary. So this is the assignment for my student. So I taught them analogical problem solving, and they come up with this. And I thought that it was interesting to share. So you can use this once you strengthen the student knowledge of how to solve linear equation. You can transfer this to solve this the side length of a triangle when you use a sine formula. Okay, so that conclude my my presentation. Yeah, thank you for listening. And now it's open to the question.